Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Professor Ed Belton with us today. Ed is a professor at Princeton University. He did graduate work at the University of Washington, which is a place some of you may have heard of. His research has been in systems, security, and system security. He's done a lot of work in browser security, and he's currently divided his work sort of 50-50 systems and security type stuff and public policy. Relating, I guess, primarily to security.
Mostly, yeah.
He's got a book coming out, same title.
Same title, yes.
As his blog, freedomtothinker.com. With hyphens.
With well, either way.
Oh, okay. Works either way. Freedom.
It's an extra $5 to have them both.
Okay. Yeah, I never went into the hype on anything. So, you can see today about new client puzzle outsourcing techniques for DOS resistance.
Thanks. This is joint work with Brent Waters, who was at the time we did this work. My graduate student is now a postdoc at Stanford, with Ari Juels from RSA Labs, and with my current student, Alex Halderman, who would make an excellent summer intern. Yep. Okay. So, so you've probably all heard and talked about this issue of denial of service attacks. Denial of service attack. You have a set of attackers who are on the top here, who are going to send requests to the server and send lots of requests to the server to use up the server's capacity. Right? And if the attackers send enough requests to the server, whatever type of request you're talking about, then they'll use up all the server's capacity, or nearly all, and the legitimate clients won't be able to get through. All right. One of the methods used to address this problem is involves client puzzles. And so the idea here is that you want to slow down the attacker by raising the cost of connecting to the server. So the client, in this scenario, is going to send a request to the server. And the server, rather than just doing the thing that the client has asked for, is going to send back a puzzle, which I've written like this, puz sub d of x. What this means is a computational puzzle such that if you do d units of work, you can get the solution to the puzzle, which is x. So the server does some computation to generate the puzzle. Now the client has to do a much more expensive computation to solve the puzzle. And then the client can send back x. And the server says, OK, you passed the test, and now I'll let you have access to the resource. There are a bunch of different constructions you can use to make these puzzles. And I'm not going to talk about that because it's fairly standard stuff. But one simple example involves partially inverting a hash function. So for example, the server might make up a random number x. And the puzzle would consist of the hash of x plus some of the bits of x. And in order to solve the puzzle, you have to do exhaustive search over the rest of the bits of x in order to find so you know all of x. All right. There have been lots of proposals to use this for different kinds of cases where people might try to flood servers. It was initially suggested for dealing with spam, so that you had to solve a puzzle in order to send someone an email. But it's been proposed for TCP connections or the use of TCP SYN buffers. So every time someone tries to make a TCP connection from a client to a server, the server might ask the client to solve a puzzle. It's been suggested for SSL connections. When you make an SSL connection from client to server, the server has to do a bunch of expensive public key crypto operations. And so you want to make sure, and so a client, by just sending garbage that looks kind of like an SSL connection attempt, can cause the server to go off and compute for a millisecond or so. And so you want to make sure that, and so that provides a possibility of an easy denial of service attack if you're not careful. And so you might want to use a client puzzle to make it harder for attackers to do that. Also, database queries, especially resource-intensive queries. And it's even been proposed to do this on the level of individual IP packets. But to make that work, you have to be really careful about your construction for the puzzles so that it's cheap enough to verify a puzzle solution that you can actually do it per packet. as far as I know, this thing that the method I'm going to talk about today is the first really practical, is the first scheme that has a hope of being practical for IP packets. All right. So what you're really trying to do here by introducing these puzzles is to change the incentives of the parties. You're trying to change the incentive of the attacker so that it becomes more expensive or difficult to do what the attacker wants to do. And in doing this, you're also, as a side effect, changing the incentive of the legitimate clients. Right? So when, and it pays to think carefully about how people are going to respond to these changed incentives. And when you think analytically about how people respond to incentives and changes in incentives, what you're doing is economics. And it turns out to be interesting to actually do a little economic analysis of this scenario. You have a server who gets to decide how difficult the puzzle is and decide some other parameters. You have a client who decides how much work they're willing to do to solve a puzzle before they just give up and go somewhere else. And you have an attacker who's willing to expend a certain amount of effort in order to have a certain amount of impact on the server and won't bother to attack if the effort to destruction ratio is unfavorable. And so you can set up the economic equations, you can solve them, find a Nash equilibrium and all that good stuff, and you get some insight about what's going on here. Some of that insight matches what you would sort of think immediately without doing this analysis, but you also learn a few things that are subtle. One of the things that maybe you learn or maybe you knew before if you thought hard is that what you're really doing here is setting up a kind of auction. Mathematically, this behaves like an auction where the server is holding an auction and the clients and the attackers are bidding for a resource where the resource is access to the server. And again, economists have a lot to say about this. There's a whole area of economics called auction theory, and you can bring in a little bit of auction theory to help explain what's going on here and to think about how this auction is actually going to play out in practice and how you might change it to make it better. And if you do that, if you think about whether this is a good auction for achieving the goals, what you decide is, in fact, it's a really terrible auction. And the reason is basically this. Imagine that you're using a method like this for web connections of some kind. So you've got a user sitting in a web browser, and the user decides, hey, I'm going to go to some website. They type in the URL or click on a link. They just made a spur-of-the-moment decision to go to this site, right? And so their browser sends a request to the server sends back a puzzle, the browser is solving the puzzle, and the user's sitting around. Right? So often, the legitimate user has to sit and wait. The person has to sit and wait while their machine solves a puzzle. The attacker, on the other hand, knows in advance which machine he wants to attack. And so the attacker can solve puzzles offline without making a person wait. The attacker uses only machine time, whereas the legitimate user often is spending human time while the puzzle's getting solved. And human time is much, much more valuable than machine time, maybe by a factor of 100, even if you actually work out the numbers, maybe more.
Is human time really significant here?
Yeah. Well, it can be. If you read the papers about this, people talk about 20-second puzzles. And if you have to solve a 20-second puzzle often enough, it's like being on dial-up. And that is enough to deter people. And in fact, you do have to when you come under attack, you do have to raise the price. I mean, it is an auction, and the attacker is willing to bid a certain amount. And the legitimate clients have to be able to or willing to outbid the attacker. And so the price may be high.
Wouldn't the time be really short when you're not under attack?
When you're not under attack, the time will be short. That's right. When the server is under attack, the time will be longer.
So two things. There's not going to be any more attacks if that works. So most of the time, it's not going to be in the attack mode. So users will wait.
Well, but the question is, it's already the case that there's only a limited number of attackers, right? And there's only a limited number of people they hate. And they can't sustain an attack for a very long time because the police will catch them eventually. They can't sustain an attack for days. And so most of the time, most of the sites are not under attack, even if you do nothing. But you don't want to be in a situation where the attacker can knock over a site whenever they want. If an attacker who controls, let's say, 10,000 or 100,000 or a million compromised machines can knock whatever website they want off the air at will, that's a bad thing. Because when you think about, again, if you analyze the economics, it's going to be expensive for the server to be prepared for the attack. The server's going to have to spend a bunch of resources up front if they want to prevent the attack. It might be that they just don't want to spend any money preventing the attack and just hope that nobody chooses to attack them. Yes?
It seems like if the result of the attack is to make the user's experience unpleasant, that may be all the attacker was trying to achieve in the first place.
Right. All the attacker wants to do is make the users not access the site.
But on the other
And if the puzzle difficulty is too long, the users go to another site. The attacker has won. The attack has worked.
Yeah.
on the other hand, one of the most expensive resources you were talking about controlling was about a millisecond. So, right. So I think it's very hard for people to get more than 100,000 compromised machines. So I was doing like little bits of math in my head and saying, okay, if each attack can use 1 millisecond of server time, but let's say I make the puzzle time 1 second, which I think users can typically tolerate, especially if it's rare, then it seems like.
Problem is that the attacker may be willing to spend 1 second per.
Okay, but so the attack. Let's say the attacker is willing. Let's say the attacker has 100,000 compromised machines. But if he's willing to spend 100,000. Let's say he's attacking somebody with 100 servers. So with his 100,000 compromised machines, he can use up all the time for 100 servers if it's a 1 millisecond cost.
If it's a 1 millisecond cost to serve.
Yeah. So it sounds like it's not clear, right? So either we need to go find a problem where the cost of the attack is more than a millisecond.
Yeah.
Or maybe maybe we already have a solution if.
Well, what we observe is that attackers actually can knock sites off the air if they control a lot of machines. So
we observe that today because there's nothing. But if we had the simple auction technique with a 1 second puzzle,
perhaps.
So maybe we're done.
It depends. Well, so let's go on. All right. So the attacker uses only machine time, and worse yet, the attacker uses stolen machine time, which is even cheaper than machine time you have to pay for. That's maybe an extra factor of 10 because the going rate to rent networks of stolen machines is about 1 penny per machine hour. At least according to the newspapers. I myself have never rented any. All right. So this is a pretty unfavorable ratio. Essentially, what's happening is that you're paying for access with this resource of time, puzzle-solving time, and the time, that currency, is much more expensive for the client to get than it is for the attacker to get, maybe by a factor of 1,000. Which means the attacker has a sort of inherent advantage in this auction. And the reason the main reason is because the legitimate client is solving puzzles online. Dan.
That's beyond a certain point. As a point, a second of machine time for the client, for a real client, is actually effectively free, right?
Well, right. So
there's this weird kind of threshold which suddenly becomes expensive.
Now we get into this, and now we get into one of the question of how you set up the model, the economic model. If you assume that the adversary can spend more to compromise more machines, and maybe compromise, if you assume that the attacker has the ability to compromise lots and lots of machines by expending more resources, then it may still be worth the attacker's while to. Then the attacker may say, well, 100,000 machines isn't enough. I'll compromise 1 million. That's going to cost me an extra, $1,000. Or whatever.
Right. I'm just saying that the original motivation for the puzzle idea was that this, up to a certain point, the real clients' cycles are free.
Are willing to put it. It's not so much free as that users will tolerate it. They won't go to your competitor's website because you did it. It's still a cost that you impose on the user. Your website is a little bit less snappy. Maybe the users don't care that much. Maybe they do. But I think it's fair to say that there is some small cost that you're imposing. Which you'd rather not say.
Yeah, I don't understand your comment about attackers being able to solve things offline. I mean, how does that work?
So an attacker can decide that right now, that tomorrow I'm going to attack Amazon.com. And I'm going to do it with a farm. Maybe you're a quote-unquote legitimate attacker where you've got a room full of machines which you're going to use. More likely you have stolen machines. But you don't have a person that's sitting there at each one of those machines and waiting. Right? The attacker doesn't have to hire a person or have a person to actually sit and wait at each machine. It's only machine time that the attacker is using. Because there's no user who's waiting for the attack to happen.
But if it's done right, you can't pre-compute an attack.
Yeah, you can't pre-compute, right?
You can't pre-compute, right. But you can compute you can compute without making it right. So you're right. Maybe offline versus online is not the right terminology. It's a question of whether there's a user there or not. For the legitimate user, though, online versus offline is the same as a person waiting versus not. All right. So this gets us to the how you can improve this auction, and that is to allow the clients, legitimate clients, to solve the puzzles offline in advance. Right? If you can do that, then the auction's more favorable. But that has a bunch of implications for how your puzzle scheme is designed. Clients are going to solve puzzles in advance. And that means that when you're solving the puzzle, the client doesn't know which server he's going to use it at. Therefore, whatever puzzle the client is solving right now has to be usable on the server that the client later decides to go to. So the same puzzle, which is being solved now, has to be able to work for many different servers. Yes?
Does this mean that the same puzzle can let the attacker attack 100 different sites simultaneously?
Yes, and we'll get to how the puzzle scheme works to try to mitigate the problems with this. Generally, attackers are trying to focus on a small number of machines while users are visiting a lot of machines. So that's not as big a problem as you might think, but maybe that'll become evident as we go on. Right. So the same puzzle has to work for many servers. Also, the client doesn't know in advance how many accesses the client is going to make during, say, during some period in the future. And so the same puzzle, it's much better if the same puzzle can work for many accesses from the same client to one server. And because you don't know which server you're going to go to yet, you can't get the puzzle from the server itself. You have to get the puzzle from some third party. From a known third party.
I assume you'll address this, but the big concern here is that when you can do this offline, it doesn't take a lot of resources to have a burst attack and just mess up a site for a minute.
I will get to that. So the solution I propose doesn't suffer from this problem. Right. So I want to spend the rest of the time talking about a solution which allows ordinary clients to do offline solving, even if they don't know where they're going to go. And the solution works like this. First of all, you outsource the creation of puzzles to a trusted service we call a bastion, which is independent of the clients and servers and can be shared by a large number of clients and servers. The bastion creates the puzzles, and they can be distributed by anybody. Clients solve puzzles, and when a client solves a puzzle, it gets access to something called a slice. You can think of, and the intuition here is that there's some number of slices in the world, like say 10 million slices. And servers will be attempting to allocate the resources fairly among the various slices. So the client is going to pick a slice at random and solve the puzzle for that slice. The client, in doing that, is going to get a token, is going to be able to get a token. So to solve for access to a slice, having solved that puzzle, the client will be able to manufacture tokens, where a token gives access to one slice on one server. And you can use that same token to access that server over and over as many times as you want. But this will allow the server to tell who's sending lots and lots of packets. Every request will carry a token. We assume that the internal routing structure is resistant to eavesdropping, so that you can just put the token into the packet. And the server is going right. Okay. So let me walk through the steps of this.
Just one more question.
Yeah.
Is there any back-end correlation done to keep me from using the same token on multiple sites?
Yeah, I'll explain how that works in a minute. All right. So the bastion generates the puzzles. Here's the bastion over here. It's going to generate n puzzles, and each one of them is going to be a puzzle using whatever standard puzzle construction you got from the old paper you read. Maybe the hash construction, for example. And I'm going to write the ith puzzle as xi. N might be 10 million in practice. The bastion, these puzzles, having been generated by the bastion, are going to get distributed to everybody. The bastion can distribute them, or it can digitally sign them, and then anybody can distribute them. And so you can, you don't have a single point of vulnerability for distribution, but you do have this single trusted service which generates the puzzles. Sorry? Microsoft, for example, right? Having built this mechanism into Internet Explorer would then do that. All right. Solving for slices, right? So the client solves a puzzle. So we divide time up into intervals. And you solve the puzzle in one interval and use that solution in the next interval. That's what allows you to do the solution offline. You have one time interval period to do the solution. Each puzzle corresponds to a slice. The client picks a random slice and solves the puzzle for that slice. And that gives access to that slice on all of the servers during the next time period. The solution can be reused as many times as you like, but if you use it a lot to access the same server, the server's accounting is going to show, I'm getting a lot of accesses in this particular slice. And then the server is going to eventually shut you off. The servers allocate resources fairly among the slices. They let everybody have as much as they want, but if the server becomes saturated and runs out of resources, it uses fair allocation, which means that it denies service first to the slices that are using the most. Mm-hmm. The servers don't identify or track individual clients. They just know how much activity there is in each slice and allocate resource fairly between them. All right. Solving and getting these tokens is a two-stage process, as shown here. So here's a client. The client here is going to solve a puzzle, puzzle number 507, which gives it this blue value, which is the solution for slice number 507 in the current time period. Now, in order to access server A, the client is going to take this solution and it's going to specialize it using the public key of server A to get this gold thing, which I'll call the token for server A in slice number 507. Now when the client accesses server A, makes a request, the client will send the token to server A. Server A will have a table pre-computed that contains all of the valid tokens for it. It's going to compare the token that it got with the thing in its table, and if they match, then it knows that it's a valid token, and the server will record the fact that there was a unit of activity in that slice. The client can, if it wants to access server A again, just sends the same token again, and the server will check again and then record another unit of activity. So the server builds up this record of how much activity there is. If the client wants to visit server B, it needs to use the public key of server B to generate a different token, this silver token, which it sends to server B. Still in slice number 507, and server B has its own table. Right. Now, this specialization of tokens to individual servers is important because the servers have a pre-computed table of all the valid tokens. And if these two servers use the same sets of tokens, then server A would know all the tokens it needed to attack server B. And server A could just hammer server B with impunity. You don't want that. So the tokens have to be specialized so that they're different for each server. But the calculation of these tokens is done online while the user's waiting. And so we designed this so that this computation to get the slice solution, the blue thing, is slow and is done offline. But the specialization to an individual server is fast, requiring, as you'll see in a few minutes, one modular exponentiation. And so that can be done online without much.
Didn't you just tell us earlier that one of the most expensive things was the HTTPS, where we had to do
for the server to do that.
For the public key.
It's expensive for the server to do that.
And here my server is decrypting.
The server is not. So the server is online. Here is just doing a table lookup. The server has pre-computed the table.
He doesn't have to do a public key. He doesn't have to do his private key operation.
He does not. Certainly not for each request. He's going to have to do a private key operation, one exponentiation, to fill each slot in this table. And I'll talk about why that's okay for the numbers of slices that I'm talking about in a little bit. Turns out that's okay. The server needs to do this once for each slice, not once for each request. And you expect to get a lot of requests per slice. And so the cost per request is not too bad. Yes?
I missed your explanation for why you need to do the customization.
The customization. Oh, the reason is this. Let's say that server A and server B were using exactly the same sets of tokens. Now server A, because it has this fully populated table of tokens, knows how to access. Server A now knows everything it needs to launch a perfectly effective attack on server B. Server A now knows all of the tokens that you need to access server B. And it could, if it leaked those to attackers, the attackers could hammer server B and using randomly selected a selection of slices.
Are you going to say why you're using public key for this? It seems like you could do this with the simple hash or symmetric methods.
Yeah. I'll explain the construction, and maybe it'll be evident why.
How is it cheap?
Actually, could I put that? Let me answer that question a little bit more. You want the client here is going to do one laborious computation per is going to do one laborious computation per time period to get this. The server needs to be able to populate this entire table of 10 million elements each time period. And so the server needs to be able to get these tokens much, much more efficiently than the client can get this completely. Right? And that's the intuition for why you're going to need to use a public key thing. So the server is going to be able to shortcut some computation that the client can't.
Okay.
Yes, that's it. Let me.
That answered the question.
Good. All right. I'm going to show you the crypto in a few minutes. All right. Right. So the servers track the resources used by each slice. Keeps a sort of weighted average of recent resource use in each slice. Requests that aren't tagged with the token are just sort of relegated to some special slice. And when resources are scarce, the server allocates resources fairly among the competing slices using standard methods such as fair queuing. And so because the clients choose their slices randomly, you get a reasonably fair allocation of resources among the clients. When an attacker is launching an attack, here we have an attacker with only 2 clients, machines, and the attacker has solved 2 puzzles, number 157 and 678. And if it wants to attack server A, it can specialize those 2 puzzles to get those 2 tokens. And then it can send a zillion requests to the server. But each of those requests has to be labeled with one of those 2 tokens. And so the server's table of how much resources are being used per slice is going to have a really big number in each of those slices. Now, a legitimate client comes along who happens to have randomly chosen slice number 507, and it's going to access the server, and it's going to get through, and it's going to be in a slice that has a relatively low traffic. So if the server's saturated and needs to rate limit accesses from some slice, it's going to rate limit slices 157 and 678. And the result is that in this particular scenario, the legitimate client will be able to get 1/3 of the server's resources, no matter how many requests the attackers try to get. So what you're trying to do here is arrange so that the attackers have access to only some subset of the slices. And then you hope that enough of the legitimate clients are randomly living in the remaining slices. Yes?
So you chose 10 million slices to be about 100 times bigger than the biggest botnets you know of?
The number 10 million, where that really comes from is is based on how many resources we expect the server to have. The server needs space to store this information for each slice. You need about 8 bytes per slice. With 10 million slices,
you have enough.
80 megabytes.
If it's expensive computation that you do once per slice per time slot.
Yeah.
If the attacker can afford to do, say, 10 of those per time slot because they're going to spend more of their machine on it, and you have a network of 1 million machines,
then you're out of luck. Yeah.
Then you can fill all the slots, right?
That's right.
And filling any more than a small fraction of them is a problem, because then that's going to affect a significant fraction of the clients as well.
Yes, it turns out that what you really want to do is have each client pick a small number, 2 or 3,
and try a couple of them,
and solve them, and then switch between them dynamically. And so then the odds get better.
Okay.
But it's true that you're going to end up with the crucial parameter is how many puzzles the attacker can solve per time unit divided by the number of slices you have. And so you want to make the number of slices as big as you can. It turns out that Moore's law is helpful here because Moore's law allows you to use more and more slices as you go into the future, because the server has more computing time to calculate these entries and has more memory in which to put them. And so you'd expect the number of slices you use to double every 18 months.
Yeah, essentially. But so does the attacker's
power. Right. But the key thing is that the attacker is solving these puzzles, and the difficulty of the puzzles can be cranked up over time. So every time Moore's law makes computers twice as fast, you just make the puzzles twice as difficult. And it turns out, as you'll see from the cryptographic construction, that the server still does the same number of cycles.
So the server's getting Moore's law, but the attacker has the same.
The attacker doesn't. Well, the attacker gets Moore's law, but you just crank up the difficulty D to compensate.
And so they still have the same number of machines, which is really the premise.
Yes, that's right. And so Moore's law, this scheme looks better and better the farther you go down the Moore's law curve.
Am I correct in understanding that the cost for an attacker of attacking 2 or more servers is only slightly more than attacking 1 server with the same amount of work?
That's right, in terms of puzzle solving. The attacker, having solved the puzzles, can then attack whatever server they want.
Sure.
whatever large set of servers they want.
That's right. But of course, if it's sort of in the limit of that, where the attacker is having a relatively low intensity attack on a lot of sites, that's actually not too bad.
Why low intensity? The expensive resources of computation. It's high intensity attack on a lot of sites.
Sure. Well, if it's the case that attackers have access to enough machines to actually barrage all the servers in the world with lots of packets, then we're pretty much sunk if we don't do this anyway. No matter what puzzle scheme you use, if the number of attacker machines goes to infinity, you're basically shot.
Sure.
All you want to do is increase the number of attacker machines that you can handle before things go south.
So, I mean, there are other kinds of multipliers. So for instance, right, a typical configuration at Microsoft, there might be 500 servers.
Right.
For one service, and right, so we can try to maintain a global blacklist for the service, but then that global that's actually pretty hard to implement in practice. And so now so either I implement this global blacklist for my service, which is hard.
Where you're blacklisting IP addresses?
No, where I keep this table.
Right. Yeah.
I keep this table in some way that. Even though people are making connections through a load balancing router to one of these 500, I'd have like a central server that was keeping this giant table.
You could probably afford to have each server instance have its own copy of the table.
So if each server instance has its own copy of the table, now they can attack 500 of my servers simultaneously.
Yes. They can attack your server farm.
They can attack my entire server farm.
And if your load balancer may be spreading the attack over your.
Yeah, but the load balancer will help them do that.
Yes.
Right. So that's unfortunate. So that's one option that's bad. Or the other option that's bad is to have a small set of special servers for storing these central tables that then become bottlenecks on my network.
That's right. Yeah.
So
we've designed this so that there are two things that the server needs to do. It needs to compute the solutions, and that you can do just in one place if you want. And it needs to store this data.
Yeah, that's
the space requirements here are low enough that you would probably just replicate the.
That's not. Yeah, so I'm not worried about the space requirements. I'm worried about the fact that they can get this 5. They can still attack. The more servers I have, the more they can multiply their attack. If I'm not using a global blacklist.
But maybe not, because remember as you add servers, the number of legitimate client requests per server is going down. And what the attacker wants to do is shut out the legitimate clients. And so if you double the number of servers, the attacker has to send you twice as many packets to have essentially the same effect. Because now now the legitimate clients need only half as much resource from each server after you've doubled the number of servers. And so increasing the number of servers does help, regardless of whether you use this scheme or not. And in fact, that's one of the main, going back to the economics of this, one of the most valuable tools that server administrators have is to just over-provision the server, so that the attacker has to use up a certain amount of resource before they have any impact at all on legitimate clients. If you have twice as many servers as you really need, then the attacker has to use up half your servers before they get any impact at all. And that raises the price of an attack by a factor of 4. That's an important defense which you would use either with or without this. All right, let me move on a little bit. So now let me show you the crypto. Here's the way it works. The Bastion publishes two things. The first is, for each puzzle, a standard hash type puzzle of difficulty D, which can be solved to get xi, the solution to the first puzzle, and also g to the xi mod p, where g and p are chosen suitably for the Diffie-Hellman construction, which you'll see happening here in a minute. The server has a private key a and a public key g to the a mod p. And the token is, for the ith slice for server A, is g to the a times xi mod p. Right? So if you're a cryptographer, you'll recognize the Diffie-Hellman construction. What the server does is takes this value g to the I and raises it to the a power, the server's private key, and that gives the server the token. Yes?
If you're not careful about which bits to publish and which bits not to publish, doesn't that speed up a baby step, giant step attack on XI?
I don't know. I haven't thought about that.
If you publish contiguous bits and leave alone contiguous bits, then you do baby stack, giant
If you're publishing contiguous bits.
X has so many bits, right?
Yes, yes.
You publish the leading bits so many, and you keep the trailing so many bits open.
Right.
You can probably do a baby step, giant step attack. Or a catching kangaroos attack.
You're right. You need to
choose the bits in a funny way.
You need to do another hash at the right place to address that.
But then the searching gets bad. You may get by with publishing all the prime numbered bits, or keeping secret all the prime numbered bits.
Yeah,
but you want to speed up the search.
The details of this are in our paper.
Okay.
But there is another hash which is in there, which I in fact left out 2 hashes. There's a hash in here, and you also hash this thing to make it small. Right. So the server does this computation. This is one exponentiation, and it's done in advance to build that table of tokens. The client has to do it the hard way, solve the puzzle to get xi, which it does in advance, and then in order to specialize it to a server, take g to the a, the server's public key, and raise it to the xi power. Right. And of course, because the computational Diffie-Hellman problem is hard, or at least we assume it's hard, there's nothing the client can't use g to the a and g to the xi to get this. It has to do it the hard way. And that's how the server gets advantage over the client. Right. So just to review the process, the client in time period j is going to solve puzzles for the next time period, picking a random slice. The server is going to compute all n tokens for the next period during the current period. The client is going to use the solution it computed during the previous period, et cetera. I talked about this. And the server is going to use the tokens it computed during the previous period. When the server gets a request, it just does a quick table lookup and comparison. Yes?
If the server does a computation, why doesn't it compromise server and I have to compromise whole server?
Because different servers have different public keys.
But you get xi.
No, the server doesn't learn xi.
Yeah.
So it doesn't compute.
No, the server gets g to the xi.
Oh, I'm sorry.
Raises it to the a power. Right. So the server could get xi, but only by solving the laborious puzzle. And that's just another way of saying the server is an attacker. So the server has one server has no advantage in attacking another server. And that's important. All right. So I've been through this. Right. So I talked about most of this. The bottleneck here is the number of slices that the server computes tokens for. That uses computing time and it uses space. As processor speeds and improve and memory gets bigger, you're going to increase the number of slices. That makes the scheme get better. You crank up the number of puzzle difficulty to compensate for Moore's law. So this gets better. All right. So here's an attack scenario. Let's run some numbers. Here we have a server farm with 200 servers. And we're going to devote another 20 servers on the side to pre-computing these tokens for the next period. So we've increased the number of servers by 10%. 20-minute time unit, and we have 10 million slices. And the puzzle difficulty is 2 CPU minutes on a typical client machine. Right? So the client, during this 20-minute period, will assume is willing to devote 20% of its CPU time to solving puzzles in the background. And we'll assume you could do that without inconveniencing the user. The attacker, yes?
So if I have my machine off, then it'll be at least that much.
When you turn the machine back on, now you don't know any puzzle solutions. And in the first period, time period, you're going to be sending your request without any tokens on it. So it's as if you were not, and so then you get segregated into this special category. And so you're going to be living in the current world for the first period until you can solve some puzzles.
Not just offline is enough for that.
If you're turned off, right?
But
if your machine is turned on, but you're at lunch, that's perfect.
But if my machine is turned on, but I'm not connected to the internet or the bastion in some way, then
right. If you can't get the puzzles, you also can't solve them. Now you could pre-publish them, but the puzzles, but that gets you in trouble. The server. Yeah. Now you worry about burst attacks.
Yes.
All right. So in this scenario, we're going to assume the attacker is willing to spend 100% of CPU time on the machines he controls, which means each attacking machine can get 10 solutions in the 20-minute period. And so with 100,000 attackers, the attacker is going to get 1 million total solutions, or 10% of the solutions. So the attacker is going to have access to 10% of the slices, and the attacker is going to completely hammer those slices. A client has 2 solutions, and so there's only a 1% chance that both of those are being hammered by the attacker. So 1% of the clients are out of luck. 99% of the clients share 90% of the resources. And the server has killed 10% of the resources. Yes?
Is it realistic to assume I can time share among these 1 million clients perfectly?
Perfectly.
The attacker?
Perfectly.
That the server can timeshare among the 1 million attackers. Like whether the client gets a slot that's been blocked by the attacker or not, is getting 1 millionth of the server resources good enough?
It depends on how many clients there are. If there's a lot of clients, then then you're going to get 1/10 millionth. But if there are 10 million clients, then getting 1/10 millionth is maybe is fine. If there's a relatively small number of clients, you're right. Then you may not get. But if there's a relatively small number of clients, actually, let's think about the limit where there's one legitimate client.
Okay.
Right. Now the attacker is going to be now the attacker is going to occupy 1 million slices, right? And that client is going to get 1/1 millionth of the server.
Okay.
So this scheme is not going to work so well on little servers where 1/1 millionth of the server is not enough.
Actually,
but if there's but on a large server, it tends to work better.
Maybe I'm asking the same question, but I'm just thinking through scenarios. I'm saying to myself, okay, what kind of problem is there where, right? I think I'm asking the same question, namely, this is enough for you may not have any blocking issues, but this is enough for the attacker to use up all the server's resources, right?
What do you mean? This is enough?
So if I've got 200 servers, my attacker can launch 200 million attacks, and now I've got 200 million attacks on 200 servers. So there's 1 million operations per server over 10 minutes, or 100,000.
And each of those operations is going to be looking at the token, seeing that you've shut off service to that.
No, the first time around, I won't have shut it off. Let's see, right? I'm just going to use it once.
So the server is going to send one request in each of these. Oh, right, okay. Right, so each server machine, if there's 200 servers, the server is going to be able to hit it with at least one request.
At least one request, okay.
Yeah. So 1 million requests over 10 minutes.
Over 10 minutes, or 20 minutes, so 50,000 requests per minute.
Per minute to each server.
To each server. That it will get served. 50,000 requests will be served, to attackers.
And if that's enough to kill you, then you'd better be pooling the solutions or having.
Yeah. So in other words, and right, most kinds of 50,000 per minute's going to be big for most servers.
Yeah, that's a good point. So so in that scenario, you're going to have to be pooling the solutions.
Yeah, and then pooling's hard in its own.
Yep. Right. Yeah. Now the good news is that you don't have to pool very quickly. In the sense, the information can flow relatively slowly from one server to another, as long as the experience of one server becomes known to the other server before too long. All right. So we have a prototype implementation of this, which works on TCP connections. The bastion is simulated by an HTTP server. The client solves puzzles and actually puts two tokens into each puzzle. One for the current time period and one for either the next or previous, so that you can deal with a little bit of clock skew. And here's the performance experiment. So let me show you. Let me first explain what's going on here. On the x-axis is system load. This is the portion of the server's resources that it's willing to spend on accepting connections. The rest of the resources presumably are being spent on actually serving clients. This is the amount of time it's willing to spend actually accepting TCP connections. And obviously, the more time you're willing to spend accepting connections, the more clients you can handle. On the y-axis, this is the number of packets or requests per second, TCP connection requests that you can send per second before you saturate the server, before you overwhelm it. And so obviously, the more time that the server is willing to spend on handling these connection requests, the more packets it takes to swamp it. And there's 4 curves here. Let's look first at the blue curve. The blue curve is a standard Linux kernel running on a sort of standard graduate student lab computer. And it's using the syn cookies feature. Syn cookies is essentially a kind of puzzle-like mechanism where the server is doing an SHA-1 hash for every connection request that comes in. And the red line here, the red line shows what happens if you take a standard Linux TCP stack without syn cookies, and instead of doing a syn cookie, you just do an SHA-1 computation for each connection request that comes in. And what you can see is that the lines are essentially the same. And what that tells you is that the thing that is slowing down, or the thing that's limiting the performance of SYN cookies, is just the SHA-1 computation. Okay. Up here, the yellow line is what you get with our scheme, where instead of doing an SHA-1 computation for every request that comes in, you are just doing a table lookup. And so now you're left spending whatever time it is that the Linux kernel takes to handle an incoming connection request. Right? And the SHA, and because this line is about twice the line below, it's about double, what that says is that by adding an SHA-1 computation to the handling of each incoming connection request, you're roughly doubling the cost of handling that connection request. Okay, so the yellow line is our scheme, assuming that the puzzle solutions are being done off somewhere else. And the purplish line here is our scheme, assuming that you're solving next period's puzzles in the background on the same server. And you can see that doesn't make much difference. All right. Let me zoom through this, because a lot of this stuff came up in the discussion. Let me talk a little bit about extensions, which we either know how to do but haven't done, or haven't quite done yet. One aspect of the system that can be a little bit inconvenient is that the client needs to figure out the server's public key. And you can get rid of that possibility by using identity-based encryption, which is a kind of public key encryption where your public key is identical to your name. And so if you make the server's public key be identical to its IP address, then you, by definition, know the server's key at the time you want to communicate with it. But identity-based encryption is a little bit slower than, it's somewhat slower than a standard public key encryption. And so we don't want to do that just yet. Moore's law is going to take care of this problem eventually. And you'll be able to switch to identity-based encryption at some point when you're less worried about the server's pre-computation time.
What do you really need ID here? It seems like what you need is to...
Otherwise, you need a public key infrastructure for letting the client learn what the server's public key is.
Slap it in the DNS. I don't know.
You can slap it into the DNS if you want. I mean, there are things you can do.
Wherever you put it, then becomes a target of attack.
Right. The PKI then needs to be defended and so on. The advantage of identity-based encryption is you don't have to worry about that. But right now, we're not willing to pay in performance. Flexible number of slices per server. Some servers may not want or need to use so many slices, and so it's a straightforward extension to let different servers use different numbers of slices. It would be nice if the bastion, rather than having to do a computation and do cryptographic computations, could just be a random beacon. That is, a random beacon is some publicly accessible source of random or pseudo-random bits. Maybe it's a satellite that broadcasts random bits. Maybe it's the hash of yesterday's stock market ticker or yesterday's New York Times. Something that everybody can get access to and is pseudo-random. And it would be cool if you could use a random beacon for the bastion, rather than having to have anybody do crypto. Now, in our paper, we talk about this more. We talk about different alternative constructions rather than the Diffie-Hellman-based construction for the puzzles. And and essentially, there are different constructions. If you want, you can have a random beacon for the bastion, but then you have to give up at least one of the nice properties that the current solution has. We don't know how. We sort of don't have the cryptographic puzzle construction that lets us have all the good features at the same time. So we have tossed the random beacon one up over the side. Early distribution of server info. Yes?
In your previous graph, how long was the time period when you had this?
20 minutes.
Oh, 20 minutes. So
20 minutes.
I need to stop 20 minutes before I can get the machine if the bad guys are misbehaving.
If the bad guys are misbehaving, right, you might be on it. You as a client might not be able to access that server during the first 20 minutes your machine is turned on. Yeah. Right. Early distribution of server info. The load on servers goes up and down over time. Right. During the middle of the afternoon, servers are busy. In the middle of the night, they have a lot of idle cycles. If the bastion distributes the information that the server is going to need 24 hours in advance, then the server can pre-compute its tokens for the next day in the middle of the night. Now, the bastion publishes two kinds of information. There's the puzzle, which is only useful to the clients, and there's the G to the X, which is only useful to the server. If you publish the G to the X early but withhold the puzzle until later, then the server can pre-compute in the middle of the night, but the clients can't pre-compute and launch a batching attack. Carl?
What happens when they attack the bastion itself?
Right. So the bastion is going to be is not going to be connected to the net directly. The bastion generates the puzzles and digitally signs them, and then you can distribute them promiscuously from all over the place. So you have to have some private way of getting the puzzles from the bastion to the places where you inject them into the net. But you're going to use some big distributed content distribution system to get the puzzles out, and you're going to let anybody who wants to redistribute them do it. So it is a single trusted service, but not as susceptible to denial of service attacks as you might worry about. All right. So the final extension here is to make the crypto faster, and one good way to do that is by skimping on the size of the keys. The keys, you're not worried about attacks where the attacker spends days trying to break a key. If the server changes their key relatively often, then the public key only needs to be unbreakable for a period of a day or a few days. And so maybe you can shrink the key size and make the crypto go faster. We haven't pushed on that really at all. All right, so that's basically it. We have this new client puzzle outsourcing technique. It allows the legitimate users to solve puzzles offline without making a user wait, and it sort of changes and it offers a sort of different set of trade-offs than you have with the existing schemes. And I'd be happy to take questions.
Well, one thing that I noticed at the beginning, you talked about the ability of the server to increase the difficulty of puzzles. Yes. To be able to deal with times when it's an attack, and therefore clients don't have to deal with puzzle solving at times of zero attack, and that seems to be gone now.
This is gone now. The client needs to spend 10 or 20% of its CPU time all the time solving puzzles. That's right. Or the client can gamble that it's not going to go to a server. The server only rate limits when it's under attack, and so if you don't want to bother to solve puzzles, then you won't be able to visit servers that are under attack, right? Which is pretty much the situation you have now.
It seems to me if you have 2 or 3 bastions and the servers alternate between serving their tickets, then compromising n-1 will still give you some service.
Compromising n-1 bastions?
Out of n, yes. So you treat tickets from bastion A, then B, then C, then A, then B, then C. Then if A and B are compromised, only the C tickets are.
If the bastion itself is compromised? Yes. Now, you're right. We've not done, we haven't really looked at much at the question of how to protect the bastion from compromise. We've assumed the bastion is going to be locked in, is going to be locked away, and there's going to be essentially one-way communication from it to the rest of the world. But certainly making it more robust in that way would be good.
If the logic for all of this is somewhere inside my server network, maybe this is kind of a silly question, but what's to stop, if I've got enough bandwidth, I can just flood your load balancer or flood, your on-ramp to the network. And, is it clear that the system or if I'm Amazon.com and I've got, a bunch of servers, accessing databases, is it clear that compute is really the scarce resource and not the bandwidth or the load balancing or any of the things that are a little closer?
Well, it's true that this method is aimed at attacks where it is the server resource on the server after the connection request has been made, which is the limiting step. And there certainly have been many real denial of service attacks that do work that way. Try to exhaust some resource on the server, whether it's TCP SYN buffers or something else. IP-level flooding attacks are a different story, or things that try to bottleneck the load balancer and so on. Now, this scheme is cheap enough that that arguably you might be able to apply it at the IP packet level, because you need to do only a table lookup for each packet. And so you might, in principle, be able to push the filtering back into the network some distance, back into your load balancer, perhaps, if the load balancer was checking the tokens. But still, a sufficient flood a sufficient brute flood of IP packets is going to sink you.
Because if I wanted to screw you, if I knew you were doing this, you could solve the flooding problem by just buying more bandwidth and making sure that's not the resource. But then I've kind of screwed you as well, right? I'm forcing you to spend a lot more. I've increased.
Right. It's another attack which we don't address, and you have to address all the attacks.
You were assuming that the table of slices is in RAM. Now, some hard drives have been known to be faster than CPU buses, And if you just rotate between the slices, you may be able to put them on a fast disk, just making the table.
Then you could have a lot more of them, but you still have to pre-compute them. And right now, the memory limit and the compute limit are at about the same point. Yes.
So you talked about things like this climate delay, and also the device that can handle all this. The obvious sort of next step would be and have somebody else do the computation for you, pre-computation puzzles for you. And of course, the next step would be to say, well, why bother with that if the bastion can actually supply these things to somebody who's trustworthy or who pays a certain fee or whatever.
You could, you could use some kind of authentication and have the bastion send.
And on the other end, we talked about just now pushing forward and maybe into the network. At what point are we sort of asymptotically approaching basically just putting in proper accountability into the internet?
Well, there's an interesting kind of, there's a limited kind of accountability that we have. Nobody knows which client is which. Right? The server is not tracking how much resource each client uses. It's tracking how much each slice uses. And that's close enough to what you want for a lot of purposes. So this is not, one view of this is that it's a sort of funny replacement for client authentication, slice authentication.
Well, or just resource usage.
Yeah. I mean, if the client authenticated itself to somebody and got a token that was unique to it, the server could apply the same kind of accounting and fairness mechanism in that scheme, and you get a similar result. But we don't have to do the identification of clients because of this puzzle, because of the slice method. But it's true that you're sort of inching toward that sort of accountability scheme. It's a limited form of that. All right.
You mentioned Moore's law as a speed up for the server.
Yeah.
Now there's also John Pollard in Britain, who every 10 years thinks of a new smart idea for breaking public key crypto. Which of them has been winning over the last 30 years?
Moore's law versus
Pollard's law.
Pollard's law.
Yeah.
There's more clever stuff to factorization.
More clever stuff
log that you could think about.
Right. And so you might have to crank up the size of your prime P.
And then you slow it down.
On that note, let's
Thanks.